So thank you very much, everyone, for being here today and coming to this container session. I'm a little emotional because Will and I are very honored for you to skip on other activities such as drinks and other forms of entertainment just to stay with us tonight. Okay, so this is, we're going to try to make it up to you with a little bit of something that is worth it. So this is a 400 level session. We're going to try to get as advanced as possible and give you a good idea of how to use basically ECS, Elastic Container Service, in production. There's going to be some theory and there's going to be some real life experience. We're going to go briefly about the microservices architecture. We're going to talk about Amazon ECS, why it fits in the picture. We're going to mention the 12-factor app, and then we're going to go through a bunch of reference architectures, pieces of technology that can help you solve problems that you might be facing or you might have faced already. Then we're going to talk about task placement as well, because it's an important part of Elastic Container Service. And then I'll leave the stage to Will. He's going to talk about how BuzzFeed did it. My name is Pierre Stegmaier. I'm a solutions architect for Amazon Web Services. I've been doing this for 3 years and a half. My subject matter expertise is in containers, surprisingly. And let's go into it right now. So microservices have been the talk of the town for a long time now. You can find a definition for microservices on many sites, including the Wikipedia. This definition here is the one that we wrote in a white paper. It mentions the fact that it is both architectural and organizational as an approach, that it emphasizes on being small and independent service. And we will dig a little bit into this as well. And all of these services are going to talk to each other via well-defined application program interfaces. And then small and self-contained teams, right? Both organizational and architectural. So there was a talk by Sam Newman, CON208. How many of you attended this talk? Wonderful. So I hope that you enjoyed it. And for the ones that didn't get a chance to attend it, it's going to be available via video very soon. And so I would recommend you watch it. And please download that white paper also. There might be a little bit to learn in there. So what we're doing is we're trying to assemble some of the best practices, both from some of the principles that were established around microservices, as well as the 12-factor app. So we used to build monolithic applications. What monolith stands for in terms of actual terminology is a single large unit, right? So in a monolithic application, all the components are tightly coupled and they're usually hard to change. It made sense at the time to build these monoliths and try to pack all the functionality within one binary or one big application. But it's, I think a lot of organizations have outgrown this method. The microservices, in comparison, are a very small atomic unit and they do one thing, they do it well. And as I said, they have a clear interfaces, they have a contract with the world, and this is the only way that you should be interfacing with these services. So why are we seeing companies and organizations move away from the monolith and into microservices? There are many reasons. I will highlight two mostly. So the first one is scaling. Because when you have to make your applications more performant and to be able to serve a larger load or bigger traffic, when it comes to a monolith, you'll have to just replicate it. And this is an easy solution, but it's not the most appropriate when it comes to resource utilization, because parts of the monoliths might be the ones that actually need more performance or more scale, but other parts might not need it. And so you're basically using a bigger box for something to contain that is not as needed, not as big. So scaling is not as efficient. Now, change is another reason, right? Because when you want to iterate on a monolith, there's a certain amount of friction that happens. So a large application is usually maintained by teams of developers. One point of friction is that when you want to use a shared library or a certain library, the developer might have to put on a salesperson hat and go around the teams and say, hey, I really want to use this library and this new version of this library, and it would make sense to all of us. Like, will you adopt it? Will you start using it as well? And then there's also the concept of merging. So merging all the code that all the teams have written during a certain length of time. It could be a merge day. Or a merge week. I've been in an organization that had a merge week. All the engineers come together and they try to have all this code be compatible with each other and remove any conflicts. And then once you've merged, you need to build the application and then deploy it into a test environment and then run some regressions testing on it. Right? Anything that fails comes back to the monolith. You have to write your code again. You have to fix what's missing, and then it goes back all the way to all the testing, and then it redeploys again. And that's for the whole application. And so microservices offer a solution to this. Amazon.com went through this journey. We had a gigabyte-sized web service, which was serving Amazon.com, and we had a full team that was entirely dedicated to deploying this binary. And so we embraced the model of microservices. It was not called microservices back then. And we identified a few characteristics that make for a successful journey. And here they are in front of you. I'm going to try to quickly identify them or explain some of them. So let's start with do one thing well. You want your application, you want your microservice to embed some of the business functions, mirror the business functions, but only the ones that make sense to the function and not more. So it's a tricky challenge to do. There's a whole book that's a good inspiration on the subject, which is domain-driven design. It's going to be very helpful identifying where the boundary is between what you should embed as a functionality within the microservice and what you shouldn't. But most of the time, your microservice is going to be a replica of a real-life function. I'm going to go clockwise. So you build it, you run it. There's this concept of a whole team owning the service, kind of soup to nuts, from the development all the way to production. So you have developers carrying a pager and potentially being pinged at 3 a.m. because the software is not running in production. So we're seeing two benefits come out of this. The first one is the developers are usually they have more ownership, and they also have more satisfaction in their job. Because they're able to actually interact directly with the customers and see their baby operate in production. And the second benefit is code quality increases. And then the next one is black box, so kind of an ominous title here, but the real idea behind the black box is each microservice is a black box to the others. And so there's a real benefit to this, which is removing coupling. Because if you're too open, if you let other services interact with components of your microservice, you're going to increase coupling. So you might be tempted to open your data layer as a microservice, open your data layer to other services, but when you do this, you are now slowed down. When you want to update your data layer or your schema, you're going to have to agree with all the teams that you're servicing that you're doing this. Whereas if you instead offer a one-stop shop API point with which to interact, you can do whatever you want behind this. You own a black box, and other services are a black box. Okay, and then, so services are also independent, decentralized. The independence the independence and the decentralization comes to the decision making, and the idea that all these teams are empowered to make the choices that they want, and I'll skip on them for now because I'm also mindful of time, and I want to make sure Will has time, and we want to try to take some time for questions. Now, the part about Polyglot is being able to speak any technology. So as a microservice, you own the technology and the technology choices. So if you want to use, if you want to change from a relational database into instead, you'd better use a key value store, then it's your choice, and you're free to do them. So we're seeing a lot of actually cool things come out of this model. If you're familiar with Netflix's open source tools, such as the Simian Army or the Chaos Monkey, so these tools come out of teams that are empowered to do what they want, what they need for their business, and then not all the teams have to reinvent the wheel. Right? So one team will potentially come up with a tool that actually has to, that they need for their own service, and by liberating it and giving it to other teams within the company, or even open sourcing it, they get a lot of traction out of this. Okay, so this was some of the key components for successful microservices. Amazon ECS fits into the picture because it is a high-performance platform for running Docker containers on a fleet of EC2 instances. And it is fully managed. And you don't have to, you don't have to stand up a whole new container management system. You don't have to scale it, make sure that it is secure, etc. All of this is done for you. It also features shared state optimistic scheduling, and this sounds really good, and all it means is that you can run many schedulers on the cluster at the same time, and this offers a lot of freedom. And ECS integrates with a lot of other AWS services, such as Amazon CloudWatch for monitoring and logging. For example, your containers can be given a Docker log driver, which is AWS Logs, and so your standard output is going to go straight into CloudWatch Logs. You can then search on it. You can put alerts on it. It's very helpful. And then helpful, sorry. And then it also integrates with CodeStar. All right, I got to pick up the pace a little bit. So we are seeing a bunch of use cases on ECS. Will is going to talk about a third one. You can see two on the screen right here. So the first one is batch jobs, because you have this large surface of compute that is ready for sending jobs to it, and each task can run as a container or a set of containers, and then when it's done, it disappears, leave the resources for another job, and you can easily scale your cluster to make room for a bigger batch or size it down. And of course, long-running apps, right? Like long-running microservices, for example. You have the benefit of health management. If a task was to fail, then another one is going to be started for you. You can easily scale out and scale in according to two dimensions, which I'll explain. And the service is AZ aware, so you're going to have out-of-the-box high availability for your service. Availability zones. Okay, so who in this room is familiar with the 12-factor app? Okay, this is really good, and it's not half of the room, though. I would really recommend that you go to 12factor.net, yes, and read on these. They're very easy to read. Each principle is less than a page long, and they make a lot of sense. Some of these, like I'll give some of examples. Like for example, processes is one of them, and it stipulates execute the app as one or more stateless processes. So stateless kind of makes sense for containers, right? Another one is dependencies. Explicitly declare and isolate dependencies. So throughout the reference architectures that I'm going to show to you today, there's going to be icons, and these icons will reference the 12-factor app. So let's go with the first one. And the first one is automatic scaling, because in the cloud, you really don't want to have to worry about whether you're servicing 10 users or 10,000 or 10 million. Right? And so you want to be able to scale, and when you're done using the resources, you just scale back. So we, at ECS, we like to recommend that you scale across 2 dimensions. The first dimension is at the app level. Your service, how many tasks are in a service? And this you can easily peg against a metric like latency or queue depth. And then the other dimension for scaling will be the cluster itself. How many instances are the host of these containers? And this you can peg against a metric that is more cluster related, such as memory reservation or CPU reservation. So in AWS, you're probably familiar with something called EC2 roles or IAM roles. It is an easy way to delegate permissions to a compute resource without having to pass API keys or, access keys or username and passwords. And because we consider containers to be just another compute primitive within AWS, equal on the same level as EC2 or Lambda functions, you can now give IAM roles to your tasks. And what this means is that on the same EC2 instance, you can have a task that is allowed to read from S3 and not do anything else. And you could also have a task that is able to write to DynamoDB, but not be allowed to do anything else. So it's very powerful, and it enables a lot of security right away. Speaking about sharing passwords, it could be that at some point you will want to delegate credentials to log into a database to some of your applications. Right? And the way to do this, it's been a problem that people embracing services and microservices have had for a while, and so there are solutions out there. But here's a solution that uses nothing but Amazon primitives. And the way that it works is that the password that you're going to pass to your service is going to be encrypted with a KMS key. And you give the task an IAM role, and the role says you can use this key to decrypt, and that's it. So basically, as the task comes up and it needs to access the database password, is going to make a request for this variable, and is going to be decrypted because you have access to the key. And this uses EC2 Systems Manager. Continuous deployment is obviously top of mind for a lot of developers. The ability to go from committing code and pushing it all the way to having your code running in production, why not, or in another environment without touching anything. And so you can do this with, you can do this all in on AWS. You don't have to, but you could send your code to code commit or even another code repository, and then through either a webhook or a notification, you would have a code pipeline trigger a deployment. And so code pipeline is going to start by sending a message to code build so that code build can start compiling, and putting together your application inside a container image and push this Docker image to Amazon EC2, to Amazon Elastic Container Registry. And then once this is done, you will have a code pipeline trigger a CloudFormation template, a stack update, which is going to update the service to ECS. And your service can run on Spot instances with like a Spot fleet, for example, which behave exactly like an auto-scaling group, but you can pay for it at a 50 to 90% discount. And the reason why we're using CloudFormation here is because it has an embedded, it has a rollback function, which can be very useful. All right, let's do blue-green deployment. So blue-green deployment is also a very popular way of upgrading a service. And the reason is because you just stand up a mirror of the application along with the infrastructure, and then you just redirect traffic. It's just running a different version of the code. So in this case, what we're doing here is we're doing the switch at the DNS level. We're using weighted round robin in Route 53 to send some of the traffic at first to the first load balancer, and then we switch it to another load balancer. But you could also do this with, so the previous solution applies very well to classic load balancer. But with application load balancer and network load balancer, you can actually do the switch at the target group level. So you got to be very careful. You got to pay attention. These two groups are going to switch. There you go. And all you do, the way you do this is just an API call. So that was a way to do a blue-green. Service discovery. What is the problem? The problem is that microservices have an average life expectancy that is very restricted. So we used to have bare metal machines, right, with probably life expectancy of months or even years, and then virtual machines, life expectancy of weeks to months, maybe weeks. And then average life expectancy for containers is actually days. And so how do they find each other if they're changing all the time? Knowing each other's IP is critical, or at least a name. And so here's a DIY way of doing service discovery using, again, Amazon primitives. And so you'll have, we're using CloudWatch, we're using the event stream that comes out of ECS. There's no polling required. Instead, you just subscribe. And as events are trickling down, you can pipe them into CloudWatch events and take action on it. And so one action could be, oh, here's a new service that just got started. Get the point of entry for these services, and then and add them to Route 53 internally hosted zone as a DNS record. But this works both ways, right? If a service gets deleted, you can also remove the rows, remove the records. But you don't have to do this anymore because very soon and announced, I think it's been announced. I hope it's been announced because otherwise you're getting a little bit, so shh, don't tell anyone. More details on this at CON 403 on Friday at 10 a.m. where Shubha is going to go into details as to how this applies to containers. But basically, Route 53 is going to support service discovery. It's going to be available later, maybe in Q1, I believe. And so basically, you'll just have to tick a box in ECS when you create a service, and the record is going to be maintained by Route 53. So you won't have to do anything. I won't talk more about this. I'll leave the interested parties to go to the session. Okay, how is Nginx an advanced concept? Well, you know, I think it deserves to be mentioned because it is extremely powerful. This is, you know, kind of the Swiss Army knife in the whole microservices world. I put a little URL there to point you to the blog post about it. All of these reference architectures are available either as a blog post or a GitHub repo. So feel free to go and Google them. The idea here to use Nginx is because you'll get both performance and security out of it, just right out of the box. So you could have an application server that is barely web-friendly and turn it into an API server. And so Nginx offers security because if you open this to the world, if you open your servers to the world, you're going to see all kinds of requests coming your way. Tools like ZMU that allow to scan for vulnerabilities. You know, there's no reason why this should go all the way to your application server. You can very much filter it right in front of it with an Nginx. And then Nginx has some really cool features like gzip. You know, you can save a lot of time by compressing the size of the packets that you send back and forth. And you can also do custom high-resolution metrics. So this is a blog post that appeared recently. You get about 1 minute resolution out of the box with a lot of our services. And with this one, you can get up to the second granularity on your metrics. And the way this works is you have a CloudWatch events clock that triggers step functions, and the step functions are going to query ECS state and insert into CloudWatch. All right, these were the reference architectures. Now we're going to go into task placement examples, and I'm going to go rather quickly into it, but I just want you to get the point of what you can do with task placement. It is quite powerful. So the most basic example is that you can indicate that you want your tasks to land on a certain type of instance, right? So let's say you have a workload that needs to be on GPU, but you have a heterogeneous cluster. You just indicate that you want them to land on G2. But you could also say that you want your containers or your task to go into a certain type, but not a certain availability zone and a certain availability zone, right? So you can target this way. Slightly more advanced is you can spread across zone and then bin pack. So this is best of both worlds because you get the high availability of having your workload straddle availability zones, but neighbor as much as possible on the same instance so that you use as few instances as possible. Then you've got affinity and anti-affinity. So you can indicate that, oh, my web servers should be neighbors of each other, or you could say something like, there should be no task that is a neighbor of my database, for example. So you can do this at runtime when you start a task, or you can just embed it within your service definition so that it always applies. And that's all for me. I'm going to leave you with Will, and I might come back on stage for a few questions if we have time.
Thank you, Pierre. Hi, I'm Will McCutcheon. I'm on the platform infrastructure team at BuzzFeed. So what I want to talk about is our experience taking a lot of the best practices, techniques, technologies that Pierre just described and building our own platform on top of ECS. Our platform is called RIG. It's a complete platform for containerized services, but sort of more than that, it's an opinionated end-to-end workflow from development all the way through to production. It comes with a handful of core services bundled with it that do automated monitoring of every deployed service and its dependencies, a continuous integration server, and an easy-to-use deploy user interface that makes it really easy for anybody to safely deploy their services. So just a quick update, RIG, we've built RIG. It's been in production about 20 months. We have 200 or more users. Those users are mostly engineers, but we also have designers, product folks using RIG to deploy services. In the time it's been in production, we're well over 50,000 deploys. As you can see on the graph, the rate of deploys is increasing. For the last month or so, we're averaging about 180 deploys a day to 400 different services running in production, 6 ECS clusters across 2 AWS regions. That's powered by 80 to 100 EC2 instances, depending on the state of our auto-scaling groups and demand. And so I'll talk a little bit about how we got to the point where we wanted to build RIG. We started like many people start with a monolith. Back in 2006, BuzzFeed was founded. There was a small engineering team that built a web application that powered BuzzFeed.com. As Pierre mentioned, that's the right way to start. You have a small team working on a small project. A monolith or a single application is certainly the quickest way to get to market, get in front of users. But over the next 10 years, the monolith doesn't scale very well in terms of it grows in functionality and complication. Your engineering team grows. So suddenly you have a whole lot of people trying to contribute code to the sprawling code base. And you get to the point where, as Pierre mentioned, you have merge days. For us, it was the size and scope of releases of this monolithic application grew to the point where we had dedicated release managers whose job was to spend an entire day, in some cases, in the best case, an entire day getting a deploy out to production. In the worst cases, a deploy would take upwards of a week to get all the way out to production, fully validated, tested, and working correctly. So this obviously slowed down the rate at which we could actually work on our projects. And at the same time, BuzzFeed, its scope expanded beyond BuzzFeed.com, and the organizational structure we adopted also changed. And so, again, like many of y'all are probably doing, we decided the answer to these problems is we'll adopt a service-oriented architecture. So we reorganized around small, self-sufficient product engineering teams, each working on independent services, sort of breaking things out from the monolith. New services were being written. And sort of the initial results you can see here. We sort of got ahead of ourselves, and our reorganization in terms of people vastly outpaced our technological sophistication and operational processes for actually managing some of this complication. And we were at the point where we had many teams building many different services, but the road to production was arduous. You had to navigate a variety of Jira ticket queues. You had to have our overworked ops team manually provisioning EC2 instances and databases and S3 buckets and security groups and stuff. The ops team and the product engineering teams both had to wrestle with not one but two heavyweight config management systems in Chef and Ansible, and as you can imagine, that's a lot of fun. And really, what ultimately, it took weeks for any new project to get from development out into production. And that, that obviously slowed us down a lot. And even worse than the lack of, the pain of provisioning new services probably was the lack of consistency that grew out of this. We had many different independent teams working sort of, again, independently, which is great, but we had, each team picked their own development environment. Each team would have a slightly different way to deploy their services. Each team had a slightly different way to have access to their logs and instrumentation and production and help debug production issues. And it meant that the operations team sort of had to relearn each new service every time something went wrong. So a few of us in infrastructure sat down during a hack week and built Rig as a proof of concept, our attempt to sort of solve some of these problems. And I'll talk through some of the things we learned in the process of building it. I think this applies sort of to anybody who's considering going down this road with any sizable engineering team. But our first guiding principle was really a focus on the engineering experience. We wanted to make it, minimize the number of times in the course of working on a service you want to throw your laptop out the window. And so that was our real focus. We wanted to make our development and deployment workflow as frictionless as possible. There's nothing too shocking about this. This is sort of the Rig workflow. But I'll sort of talk through some of the slightly interesting parts of it. First of all Rig services are in a single monolithic Git repo, which is maybe a controversial decision, but especially when you're talking about it, I showed you we have 400 services in production, 200 developers working on them. That's a lot of people in a lot of people in one code in one repo. But we think that the benefits in terms of consistency and discoverability and visibility really outweigh the downsides in a mono repo. So, we have our developer. She's going to work on a new feature for a service. So she's down a Rig dev VM, which is just a Vagrant box. Everybody's using the exact same dev VM across the company. She cuts a branch. She starts hacking at her dev VM. She runs the Rig command line tooling that we provide. Rig run to run her service locally, interact with it. Rig test to run her unit tests, integration tests, whatever test she has. When she's satisfied with it, she pushes it up to GitHub, opens a pull request. GitHub sends a webhook to Builder, which is Rig's built-in continuous integration service that's also running on Rig. Builder receives the commit, looks at what's changed, does its job, builds containers, tests them, pushes them up to our ECR registries. At that point, our developer can deploy her service. So she goes to our deploy user interface, and she only has to make 3 simple choices: service, version, and target cluster. And this sort of consistency, everybody at the company is going through the same process, even those of us on the infrastructure team. And it's important to note the same process applies whether you're talking about a change to an existing service or a brand new service that doesn't exist yet, which means we can reduce that time down from weeks to get a new service out to production, literally to minutes, from pushing your code to GitHub to having it available to deploy, to Rig actually setting it up and running in production. And that, that makes a big deal in terms of how fast our teams can move and iterate on their projects. The next big thing that we learned, we decided, our next big focus was on sort of operational simplicity and consistency. And to that end, we sort of developed these sort of abstractions. A rig service is made of a collection of things. The first thing is this service definition that defines sort of the structure, like the attributes of a service in terms of how many instances we're running, whether it's exposing a network interface, its resource requirements, and importantly, who's responsible for the service, which gets back to, you build it, you run it, like Pierre was talking about. We picked this and this way, this sort of runtime agnostic way to configure a service in this configuration file. Again, as a way, instead of asking people to write individual ECS task definitions or Docker Compose files, this sort of higher level abstraction gives us a lot of leverage as operators of this platform to both constrain the features we support and really dial in on what we know we need to support and make services more consistent across the board. And also gives us leverage to sort of sub out implementation details as necessary. So, for instance, with the announcement of EKS, we could potentially sub out EKS for ECS as our scheduling backend. And the consistency here also, benefits our developers. A developer can move from one service to another, and every service is going to have the same basic structure. If you've worked on a rig service and you jump into another one, exactly where everything is. How to see how it's configured. And this is what allows us to automatically generate solid monitoring configuration for every deployed service. We ship every service's logs directly to Papertrail. That's the logging provider we use. So if you know the name of a service, you can easily construct a query that allows you to see that service's logs. All of this is really handy especially when things go wrong and you need to jump in and potentially debug an unfamiliar service. And a really important thing, this is a lesson that we learned that's probably very obvious to everybody in this room, but what let us go from a week-long prototype to a viable platform running production workloads in a matter of just a couple of months was, take advantage of all of the good stuff that you get from the AWS platform. This is what a rig cluster looks like. There's nothing special or magical here. It's what you would expect. Everything's in a VPC. We have an auto-scaling group, filled with EC2 instances. We build immutable AMIs to roll those out to the auto-scaling group. And so, the auto-scaling group provides reliability. If a host fails, it'll make sure that it'll bring another one up, but also it provides capacity. We scale based on reservation, CPU memory reservation, like Pierre mentioned, so the clusters themselves will expand and contract in terms of demand. The ECS services themselves also can scale based on CloudWatch metrics. So like Pierre mentioned, the number of tasks an individual service can run will expand and contract sort of automatically. We get all of that from AWS. And maybe the most important thing is we kind of punted on service discovery. We took the dumbest possible approach, which is every service that exposes a network interface gets a load balancer and a Route 53 DNS entry that's a deterministic, which is not as sophisticated as some of the techniques Pierre was describing, but is really effective and simple. And you get really a lot out of the deep integration that ECS has with load balancers, where out of the box you automatically get service level health checks that'll tie into the ECS scheduler, where it'll reschedule the service that starts failing its health checks. And importantly, you get safe rolling deploys without doing any additional work on your own. So this is maybe an obvious lesson, but this is a big deal. And the last big lesson we learned is to make everything as self-service as possible. We were excited to get this out, get this in the hands of our users, all the other engineers at BuzzFeed. They loved it, so they started building a lot of services. And the first thing we built was obviously a deploy UI to make it easy for everybody to deploy their services safely. What you realize then is as your users start deploying a lot of services, suddenly your operations team is going to spend a lot of its time provisioning the data stores that are backing those services. So the next thing we built was a self-service way for our engineers to deploy data stores, RDS instances, Elasticache clusters. So the users are able to keep moving fast, but we as operators of the cluster maintain a level of control and consistency that we need. And the last thing we've built is sort of self-service user onboarding. To start using RIG, you need a set of KMS, AWS credentials that grant access to KMS keys. And so we've built a self-service way for people, any BuzzFeed developer, to log in and manage their own AWS credentials. And so I'll talk through some of the challenges we faced while building RIG. So the first one is network level access control and isolation. In the good old days, when you're just deploying services on EC2 instances, you can take advantage of, isolate your applications into separate VPCs, or if not separate VPCs, at least into isolated security groups. So only one application can access the database for that application. There's no chance of some rogue application bypassing an API and talking directly to its database. You can't really count on that when you sort of naively jump headfirst into ECS, where everything's running on a homogeneous set of EC2 instances. It's a flat network namespace. You have a variety of workloads, and on a network level, each service can essentially access every other service's data stores, which is less than ideal. You're sort of counting on the goodwill of your users to not have everything catch on fire. Our first solution to that was pretty naive. It was just for specialized workloads, we would just provision whole entire separate ECS clusters in separate VPCs. So here we have most applications are still running in a generic prod cluster, but we have some specialized application with a critical database isolated into a separate ECS cluster, a separate VPC. This works, but there's some downsides. There's more overhead for operators. We have to manage whole other clusters in the infrastructure that power them. But importantly, it's more of our end users. We don't want necessarily our users to have to care about the network level details like this. We want them to know that I'm deploying to production, not I'm deploying to this special auth privilege production cluster. So with the advent of the task placement strategies, that allowed us to build a slightly better approach, which is, we call it class host group. So within a single ECS cluster, the prod cluster here, you can subdivide the actual EC2 instances into different classes. So we have the default class where most things are going to be running. We have a workload-based class here, this worker class, where we can put async, like offline or batch applications that can fight amongst themselves for resource usage, and we don't worry about them too much. And then we can still have sort of our auth privileged set of classes isolated with isolated access to their data store, where to our users we're still exposing. They're just deploying to production, and under the hood, RIG and the ECS scheduler take care of making sure that the service is deployed to the right place. And the next big challenge we faced was sort of quickly and safely rolling our clusters. I showed the diagram earlier where we have, an ECS cluster is an auto-scaling group with EC2 instances in it. Our very first approach to rolling out AMIs, if we never change a host in place. We never go onto a host and change anything in place or deploy to the host itself. If we have to change something about the host, we build a new AMI and roll it out. And our first approach to that was again, pretty naive and simplistic, which was just to tell the auto-scaling group to spin up one new host, then tear down an existing host and wait a fixed amount of time, 5 minutes or something like that, just to give the ECS scheduler time to recognize the host was gone, reschedule any task that was running on it onto another host. That works, but as the size of your ECS clusters grows, it becomes extremely painful. It'll start to take hours to actually roll a change out to your clusters. A better approach here is we built a Lambda function that watches the EC2 event stream. So when we trigger when a new AMI is getting rolled out, the EC2 event stream will fill up with shutdown events for the EC2 instances as they're scheduled to shut down. And our Lambda function will actually tell the ECS scheduler to proactively reschedule all the tasks running on it onto another healthy host. And what that lets us do is roll our clusters in large batches while still maintaining a level of safety, a guarantee that we're not going to tear down all of the hosts that are running some particular service and cause some downtime. Another challenge we faced was sharing ECR registries. The first challenge was we wanted to make sure we had ECR registries running in multiple regions for resiliency. The fix for that is actually really simple. You just, when you Docker push, you just Docker push to every registry you want, in every region you want to have your containers in. This allows you to weather a storm. If there's a problem in one region, you can fail all of your services over. You can fail your deploy UI over to a registry in another region. A bigger challenge is one of the other things we're doing is starting to separate our ECS clusters into different AWS accounts, and it's a bit trickier to share registries across AWS accounts. You have to manage IAM permissions on like a per ECR repository level. Our fix for that again is a really simple one, which is every time we push, we simply check permissions and update them as necessary. A more sophisticated solution here would be use a Lambda function, watch for new repositories to be created, and set permissions dynamically. And sort of the last big challenge we faced is one of efficiency. Moving away from sort of managing individual EC2 instances for individual applications onto a sort of cloud of compute resources where we're scheduling many applications side by side is obviously a big win in efficiency, but there are still improvements we can make. And the real challenge here is reservation versus utilization. You can see here the orange line or the top line is reservation, the bottom line is utilization. And you can see there's a big gap here. And that's money we're kind of wasting, but it also affects sort of our ability to accurately scale the cluster up and down for demand. And sort of one of the challenges was our first approach at auto-scaling this was based on either the memory or CPU reservation CloudWatch metric. And the problem with that, with scaling on either one of them independently, is you run into deadbands where the CPU metric is telling you to scale up, the memory metric is telling you to stay put, so you don't scale at all. Our solution to that was to create a custom combined CloudWatch metric that would, and we scale based on that. And we're still tuning the math on how we combine those metrics, but we've gotten much more accurate in terms of how we scale our clusters up and down. The other big benefit that we've gotten is moving from elastic load balancers to application load balancers, which actually allow you to co-locate your services even more on hosts, along with task placement, bin packing, and spreading across regions allow us to get much better utilization. And then, I'll talk sort of very briefly about the things that we're excited about coming up next. Elastic Network Interfaces have landed and they're available. And what that enables is it enables you to apply sort of network level access control on a per ECS task basis. So what that'll let us do is do away with most of our class host groups and instead focus in just on individual services. We'll be able to have a security group attached to them that only allow that service access to a particular data store or S3 bucket or anything like that. And this is available now, and it's very exciting for us. The next big thing is we need to embrace IAM roles for tasks. This has been available for a little while, where an individual ECS task can just use the IAM infrastructure to automatically assume a role and get credentials. And that'll allow us to eliminate a whole class of secret storage that we currently have to deal with, and really reduce our sort of security surface area. And so that's sort of where we got with ECS, building a platform on top of ECS. Again, I'm Will McCutcheon from BuzzFeed, and I think we have about 10 minutes left. More like 1 minute left. Okay. Well, if Pierre and I will stick around. If anybody has any questions or wants to tell us what we did wrong, we'll hang out up front. Come talk to us, please. Thank you.